Hello everyone. This video lecture is on chapter 23, deals with amines. We don't have a lot of time, so I'm going to be hitting the highlights of this chapter. An amine is an organic compound containing nitrogen, a trivalent nitrogen, the nitrogen bonded to one or more carbon groups. Let's look at some basic ways to prepare amines. Some of these methods here are already familiar to you. In fact, the first method is just use a good old-fashioned SN2 substitution, starting with ammonia and a primary substrate. It's reactive in an SN2 type substitution. The leaving group being halogen or tosylate. The amine nitrogen nucleophilically displaces that, and under the conditions, the nitrogen will get protonated. You may have to add base to convert the ammonium ion to the amine. You can use reduction to synthesize amines. In chapter 21, we learned that amides with powerful reducing agent like lithium aluminum hydride reduce the amide to an amine. You can also use hydrogen in a catalyst there. That I haven't commented on, and so that's an alternative way to reduce amides to amines. A nitrile itself, I think I have not commented on this. If you carry out reduction using lithium aluminum hydride or hydrogen catalyst, you'll be able to convert the nitrile to the amine. Reaction 3. Now this is new to us. Start with an organonitrile compound, usually an aromatic nitrile compound. Treat that with iron or tin with aqueous HCl and heat. We call it metals are basic reducing agents. Reducing agents are agents that pass on electrons to something else, and metals have loosely held electrons. So metals are common reducing agents. You've already seen some instances of metals acting as reducing agents in our previous study. Lithium comes to mind. All right, this is going to make the protonated amine. This would make actually protonated aniline, and so to convert it to neutral aniline, you treat it with aqueous base. The last method I'll just mention for reference and edification. I will not put this on an exam, and I've not included that in the exercises, but I just want to call your attention to it. It's called reductive amination. So you take an aldehyde or ketone mixed either with ammonia or amine. There is going to be an addition of the ammonia or amine to the carbonyl group, as you recall. And you're going to get the amine or the aminim ion, and then using a spatial reducing agent, this is a modified lithium aluminum hydride, sodium borohydride. It's called sodium cyanoborohydride, and this will reduce the aminium ion to the amine. All right, let's talk about some basic amine chemistry. And amines are chemically function as weak bases or moderately strong nucleophiles. As bases, you can see an acid-base reaction if you treat an amine with an aqueous acid like HCl. HCl being strong, there's a favorable acid-base reaction where HCl protonates the amine nitrogen to the ammonium ion. The product of this would be called an ammonium chloride salt. Now also, this general rule, An amine is a weak base. Its conjugate acid is going to be a weak acid. So the ammonium ion salt, it's the ammonium ion component that will be weakly acidic. And weak acids react favorably with strong bases, so that if you took this ammonium chloride salt, treat it with the strong base sodium hydroxide, you get a favorable acid-base reaction. Hydroxide removes the acidic hydrogen from the ammonium, producing the neutral amine. Amines, like ammonia, are nucleophiles. That's similar to what we saw in the previous slide here. And they will react with substrates, primary substrates, with leaving groups such as halogen or tosylate. And so this particular action, you're going to get an SN2 substitution. Now, the major reaction that we're going to focus on is the amine functioning as a nucleophile. There's a special case where the amine reacts with a special electrophile. Here it is. This is called a nitrosoniamine. It's a kind of a cousin of a nitronium ion, NO2+. This is NO+. What one wonders, well, where does this come from? Before I go into that, I would just mention that this nitrosoniamine has resonance stability. You can write these two resonance structures. So it means that the positive charge is spread out over the molecule. The nitrosonium ion you don't find in a bottle on the reagent shelf. You have to, when you prepare it, the starting point would be, this is nitrous acid. Nitric acid is HNO3, this is HNO2. It's a weak acid. If you treat it with the strong acid HCl, HCl actually protonates this oxygen. This, we now have a potentially good leaving group, the protonated OH, break off as a water, leaving the nitrosonium ion, NO+. So that's how you basically make the nitrosonium ion. The only issue is that nitrous acid is unstable and you don't find it on the reagent itself as well. So you have to prepare it in advance. You start with something that is stable. The potassium or sodium nitrite salts are, and so that the nitrite salts can be a precursor of nitrous acid. You just treat the sodium nitrite with HCl, aqueous HCl, and basically the acid just protonates the nitrite ion, converting it to nitrous acid. Nitrous acid in solution will be stable for a couple of days. Now, this is how you make the nitrosonium ion. Basically, it's mixing aqueous, strong acid, and sodium nitrite. You could also use sulfuric acid here. In our presentation, we're going to use pretty much HCl. So, mixing these two together, you would have in equilibrium the nitrosonium ion. It would be present in at least in a relatively small amount. Now, the solution of the nitrosonium ion is going to mix with an amine. Now, the reactions that we're interested in would be primary or secondary amines, and not tertiary amines. And tertiary amines don't do very much. They just basically make a nitrite salt, and that's all that happens. So let's begin our discussion by taking a secondary amine. Now remember, primary secondary amine. Secondary amine has two carbon groups attached to the amine nitrogen. Primary amine would have one carbon group attached. So the secondary amine is mixed with the nitrosonium ion. And here's the reaction. This amine nitrogen nucleophilically attaches to this nitrogen, which has partial positive charge, giving this. This loses a hydrogen ion from this portion. And here's a new compound, a product. This is called N-nitrosoamine, N-nitrosoamine. Now, you want to be careful. I would recommend not making N-nitrosamine in the lab because it's a known carcinogen. You might have heard some publicity about the stomach medication Zantac that's used for acid reflux. And unfortunately for that company, their product was contaminated with a very small amount of, was actually kind of an N-nitrosamine. Very small amounts. The government allows a certain amount to be present, and apparently they exceeded that. But N-nitrosamines are also used by the National Cancer Institute for inducing cancer tumors in laboratory animals. So anyway, G can be either an aliphatic aromatic group. So you're going to make either the N-nitrosoamine of a that's aliphatic or aromatic. All right. Now, primary amines in their reaction start out with a similar course, and then they part company. They give something that's different than the secondary amine. In fact, here's the starting materials: the primary amine and the nitrosonium ion, and then this is the final product here. You can see this product is a far cry from that. So apparently there is a lot of chemical things that are going on here. Let's take a look, break it down. Lots of steps. Each step is basic and simple, though. First thing that happens is the primary amine nucleophilically attaches to the nitrogen, and that's what happened before with the secondary amine. We lose the hydrogen ion from this center, and this is starting to look like an N-nitrosamine, but it doesn't stop there. What happens is there is a loss of hydrogen from this nitrogen and a gain of a hydrogen on this oxygen. This loses a hydrogen ion here and gains a hydrogen ion there, and that produces this product. Can you remember that there's a spatial? These two are isomers. The conversion of this species to this species has a spatial name. If anybody remember what that is, I'll give you a hint. It's a similar thing going on to converting the enol form to the keto form. Tautomerization. Tautomerization is an isomerization that involves the breaking off of a hydrogen from one point and attaching on another point. Change the location of the attachment of a hydrogen. All right, now this is a, you call it a hydroxy azo compound, and under the acid conditions, you attach a proton to that. You've got protonated OH, which is a Levy group, which breaks off water with an assist from the lone electron pair here, swings in, this kicks it out. And there it is. This is called a diazonium ion, and that's the final product. Now there's going to be a counter ion with that. If you used HCl, it'd be called a diazonium chloride. Now the diazonium chloride, depending on what this group here is going to be very unstable or have only a modest stability. When the organic group, go back over here, when the G group is aliphatic, like ethyl, methyl, propyl, then the diazonium is extremely unstable, and it rapidly breaks down to give a carbocation and nitrogen gas. The carbocation reacts either by substitution or elimination to give a variety of products, and we're not going to really focus so much on that. What we are going to focus on is where this G group is an aromatic group, mainly a benzene ring. So can you visualize G here being a benzene ring? This is a benzene diazonium halide. Benzene diazonium halide. And that's what we're forming in this equation right here. The Phi symbol is the abbreviation for benzene ring. Now, an aromatic, a benzene or aromatic diazonium ion, in contrast to an aliphatic, is relatively stable. It'll stay around. When you prepare it, you do it at ice bath temperatures, and it'll stay around for a few hours. And the reason why it's more stable is because this aromatic diazonium, you can write resonance structures by pushing electrons around. So it has resonance stability. Now, the benzene diazonium ion is we give a full attention to shining a light on it. It's very important. And in fact, it's a precursor in a large number of useful synthesis reactions. Now, it reacts in the interesting way. It reacts in a way you might be surprised about. It undergoes an SN1 reaction to form this phenylcation and nitrogen gas. Now, the phenylcation is unstable and reactive. We make use of it by adding to it useful nucleophiles, and we get a nucleophilic substitution on the phenylcation. Now this right here is the product that we're going after. That's the useful product. So here's the idea. Here's the theme. You start out with an aromatic amine, it's a type of aniline. You convert it to the aromatic diazonium ion under controlled conditions, and the aromatic diazonium ion is mixed with different nucleophiles, and they will substitute on the diazonium ion in, surprisingly, an SN1 type substitution. Not SN2 or any other type of mechanism, it's an SN1. So one wonders, how in the world would you get an SN1? SN1 reactions are generally seen when you have a stable carbocation, and this phenylcation is anything but stable. It's one of nature's most unstable carbocations. So we wonder what in the world's going on here. And the explanation is this, is that the SN1 reaction is the breaking off of the N2 as a leaving group. The leaving group is this. This is the formula of N2 that's the component in the air, the air that we're breathing. 80% of the air we're breathing is that. Well, this is one of nature's most stable molecules. No detectable base strength whatsoever. And remember that a leaving group is a better leaving group if it breaks off as a stable weakly basic species. Well, this is about as stable as you could ever get, or as weakly basic. In fact, this is nature's most powerful leaving group. So this reaction, SN1 reaction, is favorable not because it's forming a stable carbocation, but because it has such a terrific leaving group. It breaks off so readily, and so that's what's going on there. Now, there's a whole lot of potential here for the useful kinds of products you're going to get. So we've got this list of nucleophiles. I think on the next slide I show you some examples. The nucleophiles include halide ions in different form, iodide ion in the form of potassium iodide, bromide chloride in the form of copper-1 halide, fluoride ion in a more complex form, it's in the form of fluoroboric acid. All right. Then a couple of other nucleophiles, the cyanide ion, that's in the form of copper 1 cyanide. And then hydride ion, that comes from a specialized reducing agent called hypophosphorous acid, H3PO2. All right, let's go to the next slide and show the overall reaction of the diazonium with the nucleophile to give the final substitution product. And on this one, now this looks sort of complicated because it's got a mix of these copper species in here. If you look at the product here, the N2 leaving group is replaced by OH from water. Water basically is really the nucleophile here. The copper species are there to optimize the reaction. How that's working is beyond our scope. But in olden days, they would mix just water with mild acid, and the reaction would occur, but the yield wouldn't be so good. With the copper mix, that amps up the yield a lot. Right here is a different diazonium. I'm trying to show you a variety of different aromatic diazoniums. That is, all of them have the benzene ring, and what they differ here in the substituent, what the substituent is and where it's attached. Here's a case of an aromatic diazonium where we're using potassium iodide. You can see that's over here on the list. Iodide ion is the nucleophile, and in an SN1 reaction, iodide replaces N2, and it makes this product here. Well, take a second and try to appreciate the value of this, the merit of this. It's hard to get iodine on a benzene ring. You know, when we talked back in chapter 19, the reaction, aromatic substitution reactions, where you make a halo benzene, chlorobenzene, bromobenzene. You couldn't make the iodobenzene. You know, that wouldn't work, but this one does. This is a way of getting iodine attached to the benzene ring. All right, let's start with this benzene diazonium precursor. React this with copper 1 bromide. The nucleophile here is the bromide ion. The copper in this case, when you're doing it, when bromide ion is a nucleophile, copper works better. When you're using iodide ion, potassium ion works better. Anyway, the overall reaction is simple. N2 nucleophilically replaced by bromide ion. Again, it's in an SN1 reaction. And there is this product here. Now, do you see something interesting about this particular product? And this would be named meta-bromochlorobenzene. Meta-bromochlorobenzene. You see anything that's unusual about this? Well, the thing that's unusual about it is the halogen atoms here, the chlorine and bromine, are both ortho-paradirector, and yet they're located in meta positions. If you start out by synthesizing bromobenzene and you try to attach chlorine in the meta position, that would never happen, because bromine is an ortho-paradirector. All right, and the last example is this benzene diazonium ion. Bromine's in the ortho-para position. This, interestingly, would have started out with, the starting point here would be an NH2 before it's diazotized, as you say. And that would have been made by taking just aniline itself. Aniline NH2 is a highly activating group. So highly activating, if you were to treat this with bromine and water, you don't want to use ferric bromide, or water is the solvent of choice. NH2 is so activating and ortho-para-directing, all the bromines fill all the positions, all the ortho and para, and you fully attach to ortho and para positions. Then you diazotize it and you get this diazonium salt. Well, here we treat it with this hypophosphorous acid. Now this one, I mean, if I'm a student, I would have trouble seeing that is a hydride donor, So you want to put that on your list. And because it's actually reducing agent, donating a hydride ion. And so it donates a hydride ion nucleophile that replaces N2, and there you go. There's a hydrogen there. And now what's interesting, of course, about this is that this 1,3,5 tribromobenzene, all the bromines normally orthopair directing are in meta positions. All right, now a different reaction of the aromatic diazonium salt, the aromatic diazonium ion. The principal reaction is this aromatic nucleophilic substitution, SN1 type substitution. But there is an exception to that, and that is if you treat the aromatic diazonium with a benzene that has a highly activating group, either OH or an amine group. This is phenol. You remember from chapter 19, the OH group is highly activating. It's orthopair and highly activating. Now, as I say, the normal course is for the N2 to be replaced by nucleophile. Well, this one is not a particularly good nucleophile. The main reactions of phenol are electrophilic aromatic substitution, a la chapter 19. So these two together, each of them are extremely reactive reactants, but the type of reaction they undergo are different. And so, it's like a contest. See, phenol says to the other one, I want you to react as an electrophile, an electrophilic substitution. The diazonium is saying to the other one, I want you to act as a nucleophile, replacing N2. Well, the winner is in fact the phenol. The phenol dictates what happens here and causes this diazonium to act not as a substrate in an SN1 substitution, but to be actually behave as an electrophile. The nitrogen behaves electrophile, so electron pair from the phenol comes away and attaches to the nitrogen, pushing this shared pair way onto the nitrogen. All right, so this, that's it. We're seeing this as an electrophile attaching to the pair position, which is a pair director. Now this is, of course, that's what we call the rhenium ion. And we just lose a hydrogen ion from the rhenium ion to regenerate the aromatic ring. And you see this is a very interesting product that this is called an azo type of compound. Azo type compound. This azo type compound has some interesting properties. It is basically it's an intensely colored compound, and it's used as a dye. It's a commercial dye, and textile industry has known about this type of dye for many years, and you can get different colors by attaching different substituents on either this ring or that ring. Why is it intensely colored? And well, let's see, this bears on something that would be, it's something hopefully you looked at recently in the lab activity under UV vis spectroscopy. We talked about molecules absorbing visible or ultraviolet light, and the light that's absorbed the wavelength is what's at issue, and the greater the number of groups that are in conjugation, the lower the wavelength of light's absorbed. If you just got a group with a single pi electrons kind of system, that tends to absorb in the ultraviolet region. But if you put several pi electron containing groups, if you connect them in a conjugated way, then the wavelength of the light that's absorbed is larger, and if it's large enough, it'll absorb in the visible region, and that's what it'll cause it to be colored. When something's colored, it's absorbing a portion of white light, and what's not absorbed reflects to your eye. That's what you see. So you have here, point being is that they're actually the aromatic ring conjugated, that's a pi electron group, conjugated with the azo group, that's a pi electron group, conjugated with this benzene ring, and then to provide an extension to the conjugated pi electron delocalization, you've got the oxygen lone pair pushing in. So this is an extended conjugated pi electron system, so extended that it absorbs in the long wavelength region of the spectrum, and that makes it colored. All right, now that's all we're going to do on amine chemistry. On a class on Friday, I'm going to do a special topics coverage that actually kind of relates to amine chemistry, so stay tuned on that. It's this. One of the reactions that I want to mention here is, here's the context. When we studied substitution reactions, starting from and going back to the first semester, they've all been nucleophilic aromatic substitution reactions. Then when we went to benzene, those were electrophilic aromatic substitution reactions. Substitution on benzene has always been electrophilic substitution. But notice here, we're substituting on a benzene ring that's actually now a nucleophilic substitution. Right? It's a nucleophilic substitution on the benzene ring. So this reaction is called an aromatic nucleophilic substitution. And that's what I'm going to do more of in our special topics coverage. The video lecture is going to be brief, and I'm going to look at more instances of nucleophilic aromatic substitution reactions. Stay tuned for that. Thank you for watching. Take care. Goodbye.